Hello, this is Amy Widdicombe presenting gradient-based interpretability methods and binarized neural networks. Just a quick overview. Binarized neural networks are neural networks where the weights and activations are binarized plus or minus 1, and because of this, with specialist hardware, they have the potential to be significantly more power and memory efficient than traditional networks, which we'll call full precision neural networks throughout this presentation. However, the effectiveness of interpretability methods has not been tested on these networks, even though other areas like adversarial robustness, accuracy, things like that have obviously already been tested and studied. So to address this lack of interpretability testing, we apply 3 gradient-based interpretability methods, that's gradient, smoothgrad, and gradcam to BNNs, and compare the results with those of full precision neural networks, which we call FPNNs throughout. And we present the results, which are slightly surprising as an example of why interpretability techniques should be tested on a wider range of networks rather than just the few that are traditionally used in interpretability method papers. Just a quick introduction to binarized neural networks. These are networks where the weights and activations have been binarized using the sign function usually to plus or minus 1, and they use pseudogradients for backpropagation. So this is the sign function, and this is the gradient of the sign function, which, as you can see, is unusable because it's 0 almost everywhere. So instead, they approximate the sign function to a function like this example, the clip function, and use the gradient of that instead, which is called, this example is called the straight-through estimator, but there are other pseudogradients. And this use of the straight-through estimator or other pseudogradients is one of the reasons we think that gradient-based saliency methods could perform differently for binarized neural networks. So our first set of results, these are using the gradient technique, and these are the BNNs, these are the full precision networks, and as you can see, we have a range of networks here of both kinds, and there doesn't seem to be, just purely by visual comparison, the gradient method seems to work as expected for BNNs, and the results look pretty similar, again, by visual comparison. So yeah, here these results are again. It'd be hard to conclude anything, in particular from them. So by visual comparison alone, the maps from full precision networks and binarized networks look quite similar using the gradient saliency method. So from this, we can conclude that the gradient saliency method still works, or appears to work, even with the use of pseudogradients. So here are our results for smoothgrad, which is a bit more surprising. So smoothgrad uses, similar to the basic gradient technique, but applies random Gaussian noise, and takes an average across several samples to get a more smoothed map. Here are the results at 20% noise, which is sort of what's, 10 to 20% is what's recommended in the original paper. And these are the full precision networks, and these are the binarized networks, and you can kind of see that the saliency maps of BNNs are less clear and noisier. Just a little close-up of a few of them. So the thing you can really notice with the BNNs is that the backgrounds are quite bright, and that's because of attribution falling on, kind of noise on the background, significantly on the background. Whereas, for the full precision networks, that's less the case. You get more of the contrast, the dark background, and more kind of features of the object, like the legs of the horse and the ears and etc. coming. So the saliency maps appear noisier, less clear, for binarized neural networks, and we followed up with some other experiments looking at saliency maps produced at different noise levels. So binarized neural networks degrade to almost random noise, basically. The saliency maps become almost random noise before even getting to 50% noise perturbation, whereas the full precision networks keep some shape of the object. And the optimal noise perturbation for binarized neural networks seems to be much lower than for full precision networks, at around 2 to 6%, which compares to the 10 to 20% recommended in the original paper. A possible explanation for this is that binarized neural networks are more noise sensitive, which is discussed in Lin et al., where they look at binarized neural networks and other quantized networks' sensitivity to adversarial attacks and other noise perturbation. So here are results for GradCam. Again, sort of surprising. So the GradCam, the original work, GradCam claims that the technique should work for any convolutional neural network architecture. However, from these results, BNNs seem to be an exception to this, even though they are, a convolutional neural network architecture. Yeah, in some cases, so only QuickNet, this line here, seems to work as expected, highlighting the objects as expected, whereas some of the others, MeliusNet seems to be quite random, and real to binary net, you have this blank example. So yeah, BNNs, produce kind of strange maps. This is just a close-up of, the ResNet, which is performing as expected, highlighting the object. Whereas MeliusNet kind of these strange shapes and, attribution around. So binarized neural networks produce strange maps using GradCam. We start to try and explain this. One possible explanation, looking at the original paper, which justifies the use of the last convolutional layer as the best place for, the best compromise between spatial and semantic information. It could be that for binarized neural networks, this information is just stored differently, or for some of the binarized neural networks. Another thing we look at is the ReLU. So this is the equation for GradCam, and this is this sum. Basically, they use the ReLU to cut out negative values. They justify this with kind of ablation studies showing that without the ReLU, you get maps which highlight the object more, basically. Whereas we've sort of found the opposite, that by removing the ReLU and flipping the maps, the more of the object is highlighted in some cases, particularly, MeliusNet, which we saw on the previous slide, which doesn't seem to highlight the object. If you remove the ReLU and flip the maps, you get an explanation which highlights the object. So it could be that these negative values, this sum, are actually informative for binarized neural networks. So just a quick summary. We've looked at how 3 gradient-based saliency methods work when applied to BNNs. For 2 of those, smoothgrad and GradCam, there's some difference in behavior from what is expected. And kind of the main takeaway we hope from this is that this is kind of an example of where well-known interpretability methods behave differently from what we'd expect or fail, even if they're supposed to, like GradCam, supposed to work for any CNN architecture. And we hope that future work designing and testing new interpretability methods will consider this, will consider that maybe they should be tested on a wider range of network types rather than just, the standard VGG or ResNet. Thank you.